Hi everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 4 of linear algebra. So like in this lecture what we will study? We study about the transpose and trace of a matrix. What do you mean by transpose and what do you mean by trace? Transpose I think I have given a bit of brief about it, but we'll do this in detail in this lecture. And about the inverse and adjoint of a matrix. What do you mean by inverse and what do you mean by adjoint of a matrix? And questions, like one question I will give as a homework to you. But before going into the this lecture, I want to like tell you like what happened in the previous lecture. What did I miss? Like there was one question, right? Yeah, this question, like I forgot like what was the trick in this. So the trick in this was I was doing it wrong because I was adding with the column 3. Instead I needed to add with the column 1 or with the column 2. Okay, if I add with column 1 all of the 3 columns, then it will be 1 1 1 and 2 columns will become same, and if 2 columns are same, then obviously determinant will become 0. So that's why sometimes these tricks are tricky. Basically we tend to forget like what things to apply. So yeah, sometimes we see it, sometimes we don't. So you always know that you have a backup option from basics you can always do it. Just make the maximum number of zeros and that's it. Okay, so either way you will get to your final desired answer. Also one thing, like I was explaining you what operations we can apply to the rows and columns, right? What operations we can apply here. Where is it? Yeah, here, right? So I forgot to explain the last one. We obviously cannot change row and column at the same time, and also we cannot change the row, okay, while changing the row. Also we cannot change r3 while we are changing the r3. Okay, like basically what do you mean by this? So I'm changing r3 with 3 times r3 minus 4 r1. We won't be able to do this. Here my new determinant won't be equals to my old determinant. Okay, here also my new determinant won't be equals to my old determinant. So we are not allowed to do all this operations. So what my recommendation is, do not use the same row and or slash column for the more than one in one operation. Also like the same row also you should not multiply 3 or divide by 3, anything do that. Okay, that row should remain untouched. Other things you can multiply with 4, then subtract, all those things we can do. Okay, linear combination, but that row whatever you are applying it to, it should remain untouched. So yeah, that was like I forgot to explain this in the previous lecture. So yeah, let's now start with this lecture about the transpose of a matrix. So what do you mean by transpose of a matrix? So basically the transpose of a matrix is obtained by changing its rows into columns. Or equivalently its columns into rows. Okay, either you can change its row into columns or columns into rows. Either both way you can do. Okay, so what do you mean by that? So I will explain you with example, but do remember this is like operator and this is valid. Everything is recording, right? Sorry for that. Let me just check. Yeah, everything is recording. This is like operator and this is valid only for valid for both square and non-square matrix. Valid square and rectangular. Oh no, rectangular matrix. Okay, so this is valid for both square and rectangular matrix. So I should write here both. This will be difficult now. Why is this coming up? Okay, this one will. Just hold on a second now. Let me fix this thing. Okay. So this is the first point about this transpose. In linear algebra, the transpose of a matrix is actually an operator. As I told, it's actually an operator that flips a square matrix over its diagonals by switching the row and the columns indices of matrix B, producing another matrix. So I will like once we do an example, we'll understand this. And if a matrix A is of order m cross n, then the transpose of the matrix A dash, okay, they are denoted like A dash or AT, I will show you the symbol also, is of the order n cross m. Okay, these are the 3 points. So let's first understand the symbols of it. Basically the rows and columns are getting interchanged over here, nothing fancy. Symbols. So symbols is basically A transpose, A dash, A small t, okay, or you can give like ATR, okay, you can write like ATR also, like in question these may come. So what do you mean by A transpose? So A transpose, where rows and columns are getting interchanged. So if per se my matrix is 1 2 3 4 5 6, okay, now what will be my A transpose in this case? My A transpose simply will be, this is what is the order of this? This is 2 cos 3. The order of this will be one, like what is happening here? I will change my rows into column or columns into row. So I either way you can do. So this is one column, right? This is, let me change the color. This is one column. So what I will do, I will put this in this row, okay, then I have another column, then I will put this in this row, okay. So it will be 3 4. Let me just mark this in white only. Three 4, and then this is 5 6 actually. So this will be like this. I made this a bit longer than it was required to actually. So basically this will be the second column which has been made a row over here, and then the third one. So let's take another different color. So yeah, so this is 5 6, okay. So 1 2 3 4 5 6, 1 2 3 4 5 6. So basically it is A transpose. And what is the order of this? Order of this is 3 cross 2. As you can see right, the orders got swapped. Also, like the columns become rows, or what you can say, the rows become the column. You can say it like this also, whatever suits you. Now let's what about this point where it is talking about that flips the square matrix over its diagonal element. So let's take a square matrix. So obviously we can't talk about diagonal elements for a non-square matrix. So let's take a 1 2 3 4 5 6 7 8 9. So what will be my A transpose? This is first example. This is second example. What will be my A transpose now? So my A transpose, what I can say is basically this, right? This will be totally flipped to a column. So and this will be 1 2 3, like this row become a column, then again this row will become another column, this again row will become another column. So this will be 4 5 6 and 7 8 9. Okay, so this is my A transpose. Basically what you can observe is, if you make a like this diagonal, okay, these are the diagonal elements, right? So here what happened, 2 3 6. So 2 3 6, if you observe this carefully, 2 3 6 are exactly over here, exactly over in this area. Previously they were on the upper triangle, now they are on the lower triangle. Or you can say 4 8 7, they are in the lower triangle, they become in the upper triangle. So basically they got flipped. So that is what this second point is talking about. And this order, we already seen that they're flipping the orders right here. And like obviously for a square matrix the order won't change, 3 and 3 got flipped, so it is 3 and 3 only. Okay, so what are few properties of a transpose of a matrix? So first property is, if you do addition, subtraction, and take the whole transpose, you can take the individual transpose of those matrices and do the same operation, addition or subtraction. You can do that. Okay, so like, what is the expansion of this? What is the expanded form of this? Like, the expanded form of this will be for three matrices, right? A plus minus B plus minus C whole transpose will be equals to A transpose plus minus B transpose plus minus C transpose. Okay, plus minus C transpose. Now AB transpose is equals to B transpose A transpose. You can do it like in example, and you will see that AB transpose will be equals to B transpose times A transpose. Basically, you take this transpose inside, okay, and you just swap them. Okay, swap the multiplication. Okay, I hope you like, this is a property, you have to remember this, and this is pretty simple to remember. Now A transpose determinant is determinant of A, because like either you open through about the row, okay, for calculating the determinant, or open about the column, it doesn't matter. So basically only the row and columns are getting interchanged, so it won't, like, determinant won't change for A transpose. Now transpose when applied to a matrix has highest precedence than multiplication and addition operations. So here, like, what does this mean? Basically it is talking about the precedence, it is talking about the priority, which one has higher priority. So let's say I have a operation that I'm doing AB transpose. Okay, what does this mean? What does this mean? Does this and this mean same? Okay, do these and these are same? They are not same. Why? Because if transpose is applied, right, we won't consider multiplication first, we will do the transpose operation first, because transpose when applied to a matrix has higher precedence. So this is the rule that we follow. So basically first what we'll do, we'll take the transpose of this B matrix, okay, then we'll do the multiplication, So like, this is one example. I can tell you another example also. What is another example? Basically this is more simpler. So you have A plus B transpose. Now obviously you won't do the addition first. What you will do? You'll do the transpose first. So here A plus, you will first do the transpose, then you will do the addition. So obviously always transpose has the higher precedence over multiplication and addition operations. So this is a few key points about transpose. Now let's learn about the trace over matrix. So what is a trace over matrix? So trace over matrix of a matrix A is defined as the sum of its leading diagonal elements. So what do you mean by sum of its leading diagonal elements? Basically, if I have a matrix A over here, okay, and this is 1 2 3 4, so what will be the trace of A? It will be simply sum of the leading diagonal elements. What are the leading diagonal elements? These are the leading diagonal elements. So just simple concept, nothing in detail. So 1 plus 4 equals to 5. So that is the simple definition of a trace. Now wherever diagonal comes into the picture, that means it is only valid for a square matrix. So only valid for square matrix. Okay, it is only valid for a square matrix. Sorry. Now, like, let me write this definition in a more precise manner. So basically, trace, okay, also known as, this is also known as spur, right? This is also known as spur actually. So like, generally they don't call this name, but spur, they can also say that. What is the spur of this matrix? Trace and spur mean the same thing. Okay, so they are just terminologies, nothing else. Trace of A can also be written like this tr of A, okay, which is equal to the sum of the leading diagonal elements. So let me take a generalized case over here, which is like a 3 cross 3 3 cross 3 matrix, or just right. So here the elements will be A11, A12, A13, A21, A22, A. Let me make this. Okay, so the trace will be simply a diagonal sum of diagonal elements, right? Sum of diagonal elements. Simply in this case, it will be equals to A11 plus A22 plus A33. Okay, so in this case, my trace, like for a generalized case, what will be my trace formula? Trace will be equals to sum I equals to 1 to n, where n is the order, okay, and I, okay, because like I means the diagonal elements, where my row and column are same, number of row and column are same. So this is the basically formal like equation of trace of A. Okay, no need to go too much into the details of this, just this is about the trace. Now what are the few properties of trace? Basically, if you are finding the trace of A plus B, then it will be distributed. So like simple only, because like A plus B, the diagonal elements are simply getting added. Okay, diagonal elements are simply getting added. So if you find them individually and then add them, or you first add them and then find the trace, both of them are same. Okay, and here one thing to note here is A and B are both square matrix. You can extend this, right? You can extend this like what I will say is, you can write this minus also. I forgot to write minus over here, and you can do this for 3 matrices also. So let me bring this down a bit. So trace of A plus minus B plus minus C equals to trace of A plus minus trace of B plus minus trace of C. Okay, so this is one case. Now what is trace of K times A? K is a simple scalar. So if you multiply K with a matrix, what will happen? K will get multiplied with all of the elements, so also with the diagonal elements. So if you add those two, you can just take K common, right? K common. So basically that is what this is saying. So you can take the K common, and trace of A will remain same, because that is the main thing. And trace of AB will be equal to trace of BA. This is why. And also K is here scalar. Remember, K over here is a scalar. K over here is a scalar. Okay, and what is another thing? Another thing is that trace of AB equals to trace of BA. Now here, why is this the case? You can cross verify the if you do BA or AB, A times B or B times A, we know that this is not necessarily always equal. AB equals to BA, not necessarily, but the diagonal elements will always be equal. Okay, so diagonal elements will be equal, hence this relationship is valid. This is a very good relationship. Okay, this can come in examination. So here diagonal elements remain same. Okay, also trace of A equals to trace of A transpose. Why? Because again here also diagonal elements don't interchange, because if you swap this 1 1, they are still 1 1. If you swap this 2 2, they are still 2 2. If you swap this 3 3, they are still 3 3. So here also diagonal elements remain same. I will write this for both of this. Okay, so this was about the trace of a matrix. Now let's move to the main topic of this lecture, that is the invertible matrices. So a matrix is invertible, like a matrix A of a dimension n cross n is called invertible if and only if there exists another matrix B of the same dimension such that A times B equals to B times A equals to IN. Okay, inverse. Sorry, equals to identity matrix I. We have already learned about identity matrix, which is simply like a 1. Okay, inverse, I hope you got a bit of idea, like from decimal system, what is the inverse? What is the inverse of 3? It is 1 by 3. Something similar to here. Something similar is happening here. So basically, 3 times 1 by 3 is what? 3 times 1 by 3 is what? 3 times 1 by 3 is 1. That is what this is also trying to say to us, like in matrix language. So let me write inverse of 3 is what? 1 by 3. So how do you know it is 1 by 3? Because basically what you do is you multiply 3 into 1 by 3 and you get 1. Okay, you get 1. So that is how you find the inverse, right? So here also it is, the definition is something similar here only. Okay, the definition here is something similar here. So now what else? Now from here, can we say like what is inverse actually? So basically my B, this B will be A inverse. B will be A inverse. Okay, B will be A inverse, and this is how the inverse is denoted. Okay, just like here, what will be 3 inverse? How will you denote 3 inverse? 3 inverse will be denoted like this: 3 minus 1. Now 3 minus is 1 by 3, that we know. Okay, but we don't write 1 by A over here. We don't do division in matrices. We don't do division. Okay, that's why we just simply write it like this format. So yeah, B is equals to A inverse. This is my inverse matrix. Okay, so these are the things. Now what are few things you have to keep in mind? So few things you have to keep in mind is, first, this is valid for, I will write this in the next page. Okay, no. Okay, yeah. So first point is, this is valid for only square matrices. Why is this the case? So basically identity matrix is always square matrix. So if this is a rectangular matrix, that is fine, but this cannot be rectangular matrix. Also there needs to be determinant for finding the inverse. I will explain about that. What is the formula for inverse? I will explain about that. So why am I saying this? So let's say I'm just doing this in rough. A is some m cross n and B is some n cross p. Okay, so now if you multiply this, you should get I of n, right? I of n, or whatever order, like something x cross x, right? Whatever order. Now you multiply this is okay, we can multiply this. Okay, multiplication is valid for this. So my final order will become, I will take the outside this row and this column m cross p. Fine, but this has to be square, this has to be square, right? Because it is equals to the identity matrix, and which is always square matrix. So basically m has to be equals to p equals to x. Fine, now I have to operate this operation also, b into n cross p into a into m cross n. This has to be also a valid operation, and I need to get again identity matrix x cross x. So here in this case, obviously this multiplication has to be valid. If it has to be valid, then p has to be equals to m. So p equals to m, okay, which is equals to x, not x, p has to be equals to m basically. And we know that here in this case previously m equals to p equals to x. So we got this from here, we got this information. I'm just doing this in rough to explain you a bit of concept. And obviously we'll take the outer rows, which is n cross n. The inverse order will be n cross n, which has to be equals to x cross x. So x equals to n, and you put over here. Okay, so p equals to n, m equals to n. So everything is equals to n. So definitely that's why this is only valid for a square matrix. Okay, according to our whatever rule we have set, right? Whatever definition we have set, it has to be a square matrix. So this is the first case. First key point that I wanted to tell. Let me write here key point over here. Do you have any key point? No, let me just put this. Okay, now let me draw this in actually white. Now what is the second point? The second point is A has to be a non-singular matrix for inverse to exist. A has to be a singular matrix for inverse to exist. Why is this the case? Because like I hope you have studied in your 11th and 12th, and I will say you here also that what is the definition of an inverse, like how do you compute the inverse? So this definition we know, but how do you compute the inverse basically? So you compute the inverse something like this, that you write A inverse equals to adjoint of A divided by determinant of A. Now this cannot go to 0. If this goes to 0, then like this is, we don't know, something upon 0 is, we don't know. Okay, so undefined. So basically that's why A, the determinant of A cannot be equals to 0. This is the first thing. So if basically determinant of A is 0, then inverse doesn't exist. Obviously I will say you the definition of what is adjoint of A. I will just say you. So if determinant of A equals to 0, then inverse doesn't exist. Okay, so then inverse doesn't exist. Now let's come to the adjoint of A. What is adjoint of A? So basically adjoint of A we can write like this, that adjoint of A will be equals to the matrix of cofactors whole transpose. Okay, adjoint of A is basically matrix of cofactors whole transpose. Now we know what is cofactor. So cofactor of each of those elements, and we write those cofactors in in matrix format, and we take the whole transpose of that. So basically what is the cofactor matrix? So what is matrix of cofactors? Matrix of cofactors I can write like this, which is equals to the Cij, okay, which it's noted like this, and it is simply -1 times I plus j into the minors of those particular element. Okay, so these are what I hope you like remember, right? We just learned this in the previous lectures. These are the minors. Okay, now what will be simply my adjoint of A? My adjoint of A will be simply the transpose of this. Adjoint of A will be simply the transpose of this. Okay, so this is what my adjoint of A is, and my inverse of A I just wrote over here is basically adjoint of A by determinant of A. Now I will obviously do few examples about adjoint of A, and from there we'll understand, okay, how do you find the adjoint of A. So basically what is the adjoint of A for true cos 2 matrix? So let's do it with a true cos 2 matrix. So let me just put this in a box. So basically you can write it like this, that let's say my A matrix is AB CD. Okay, now what will be the adjoint? Basically, first you find the cofactors of each of this. So what will be my C A basically? Okay, so what is the cofactor for this? This is the first element. Okay, like 1 1. So let me mark the rows and columns. So like let me mark the signs anyways. Plus minus plus minus. So this is plus 1, and what is the minor of this? This only D, right? Only D is the minor. So D will be here, and sign is positive, so it will be positive. Now what is the minor of this? I cancel this row and column, and C is only left, and obviously I have a minus sign over here. So this will be minus B. Again I do the same thing for this D element. This will be minor will be A, and I have a plus sign over here. So this will be plus D, not D, sorry, plus A. And again I just cancel out this row and column. I have left B, and I have a minus sign over here. So this will be minus C. Okay, so this is my adjoint of A. This is my cofactor matrix. Cofactor matrix. Now for adjoint of A, I have to take transpose of the cofactor matrix. Okay, if I take the transpose, my rows, these columns will become rows. So this will become D's, D minus C, and minus B and A. Okay, just hold on a second. Am I doing something wrong? Yeah, I made some mistake over here. Sorry. I just cancelled this like element. This should be C, right? This will be C. So this should be C, and this should be B. Yeah, my apologies. So this will be B, and this will be C. Okay, so this is after taking the transpose. Like I missed that point. Okay, so now what is my this inverse basically? What is my inverse? So A inverse equals to adjoint of A by determinant of A. Now obviously this equals to D minus B minus C A. Okay, and we have to divide by determinant of A. Determinant of A is what? For this, what is the determinant of A? AD minus BC. So AD minus BC. This is like a scalar, so you can write in front 1 by AD minus BC. Just hold on. And you can simply take a copy of this. Okay, so this is my A inverse. Okay, so like, is there any shortcut for this? So we did so many processes, right? So many processes. So is there any shortcut? So what is the shortcut? Like I hope you already know this, but if you don't, I will tell you what is the shortcut for a 2 cross 2. Also I will tell it for a 3 cross 3 also, for A inverse. Okay, so the shortcut basically is that if you have a matrix like this, then basically what do? You basically swap these two. Okay, I will swap these two and change the sign of these two, and obviously divide by the determinant. So and divide by the determinant, right? That is what you do. So basically here what will be my A inverse? A inverse will be simply these two elements are swapped. The principal leading diagonal elements are swapped. So I will write this over here. Swap the leading diagonal elements. Okay, swap the leading diagonal elements. So if you swap the leading diagonal elements, and what do? Change the sign of diagonal elements. And then you divide by determinant of A. Okay, divide by determinant of A. So basically this will become something like this. This will become this swapped thing. This will become dA minus B minus C, and this will be simply 1 by AD minus BC. Okay, so this is what my A inverse is. I won't go much into this, so I will tell you about the 3x3 shortcut also, but before that let's understand the pre-multiplication and post-multiplication, which is very important for matrix multiplication. Okay, so basically if some A and B are given, okay, now you want to pre-multiply. What do you mean by pre? Pre means before. So I want to multiply before. So that is what pre-multiplication. So if some statement comes up, or like obviously statement won't come up, but you have to understand this, that this is one pre-multiplying equation 1 like this by A inverse. Okay, if I'm pre-multiply by A inverse on both sides. Okay, so basically what will happen, pre-multiplication means this will come in front, A inverse will come in front. Okay, I'll just copy this, and this will be so like what is A inverse times A? So that is a definition, right? So I forgot to write over here. So B is A inverse. So what I can say is, if I replace B with A inverse over here, what will happen? And the thing that will happen is, I can further derive this actually. Just hold on a second. So just hold on a second. What I can further write is that I can replace B with A inverse, right? So B into A inverse equals to A inverse into A equals to IN, identity matrix. So this is what I was trying to get at finally. Okay, so basically what we'll do is, where was I? Here, right? So here A inverse times A will be identity matrix 1. So 3 times 1 by 3, 1. So that is what we are doing over here. So A inverse times A will be I only, and I times any matrix is that matrix itself. So 1 times 3 is 3 itself. So I times this also is A inverse itself. Okay, so like we obviously got here obviously that my B equals to A inverse. I already actually solved it previously, but still, like from here also you can understand what do you mean by pre-multiplication and post-multiplication. Now let's understand the post-multiplication. So if I say this statement that post-multiplying, let me write this a bit better actually. So now doing the same thing, post multiplying the equation 1 by A inverse. If I do the post multiplication, what does mean? Post means after, right? So obviously this will be equation 2. I'll change this equation now. Already also is equation 1 only, so same equation only. Okay, post means after. So this is at the end. At the end I will multiply with A inverse. So if I multiply with A inverse, so this I should copy. this is A inverse. Now this becomes what? Now basically, sorry, one mistake I made. I should multiply by B inverse, not A inverse, to cancel things out. So this will be B inverse instead of A inverse. Basically I want this relationship, right? B into B inverse. So again, it's the same thing, only B into B inverse will be what? Identity matrix. So this will be identity matrix A. You can skip through this if you already know, because first few lectures are pretty easy, so you can watch them in 2x. Okay, and this is B inverse only. So this will be A equals to B inverse. Okay, so basically I just wanted to say you what does post multiplication and pre multiplication mean, and we got these two relationships. Okay, so basically B will be equals to A inverse and A will be equals to B inverse. So basically inverse of inverse is same element itself. So yeah, that is one thing. Now I told you about the post multiplication. Now let's understand the shortcut for a 3x3 matrix. Okay, I will tell you about the shortcut for a adjoint and then we'll directly do it. Okay, so basically what you have to do is first copy the whole matrix. I will write steps over here. So copy the whole matrix, copy elements of the matrix, then copy 2 rows and columns of the matrix. Okay, so what will do, basically you will copy the 2 rows and columns, and how will you paste it? You will paste it at the end. Basically you will paste it here. Let me color this differently so that you will be able to understand. And I will copy the first 2 rows and first 2 columns, right? And this is copy. I should write here first 2 rows and first 2 columns. Copy the first 2 rows okay. So then what you do, then basically you cross off the first row of the, I should write it, paste it to the end, paste okay, I should write this in white. Towards the end. I'm just talking about the shortcut because like mostly if you have to find the inverse, mostly they will give for 3x3 matrix. For 4x4 it will be very difficult. That's why just this shortcut if you remember, and you're good to go for finding the inverse. Paste them towards the end. Respectively. Okay, so you paste them. Now you cross off the first row and the first column of the resultant basically what to say, array. Okay, resultant array. You eliminate the first row and column of the resultant array. Okay, so after eliminating them, then what you will do, then you will find the adjoint. So from here you will directly find the adjoint. Okay, so and which is with the sign. You don't need to worry about signs also. No need to worry about signs. So what will be my adjoint of A? So what you will do is basically as adjoint of A is transfer of the cofactors, you are basically finding the cofactors here through the shortcut directly without any sign change. So if you move vertically, you have to write here horizontally. Okay, so what I will write, so expand expand vertically and right horizontally, or vice versa. Okay, or you can expand horizontally and right vertically. Okay, so what do we mean by expansion? So let's expand few things. So how do you expand? So we'll start from this, right? We'll start from this. So we'll expand like this: 3 times minus 1 minus 4 times 4. Simply how you use to compute the minor, right? So this will be 3 times minus 1 minus 4 times 4, which is minus 3 minus 16, which is minus 19. So this will be minus 19. Okay, now if I'm moving in this direction, let me use another color. If I'm moving in this direction, right, then I will move in this direction. Very important. So next is this 4 times 6 minus 1 times 2. So 4 times 6 is 24 plus 2, which is 22. 24 plus 2, which is 26. So I'm moving in vertically, so I'll move here horizontally. So this will be 24. Now again 2 times 4 minus 6 times 3, 8 minus 18, which is minus 10. So minus 10. Again this has been finished. So I'll again start with this new column. Basically again I'll start with this new column. Okay, so again I will do the same thing. 4 times 5 minus 1 times 0, which is 20 itself. Again 1 times minus 1 times 1 times minus 6 times 5. So this will be minus 1 minus 30, which is minus 31. And this is 6 times 0 minus 1 times 4, which is minus 4. Now again we start from here, right? 0 times 4 minus 15. So this will be minus 15. Then 5 times 2 minus 4, which is 10 minus 4, which is minus 6. And then 3 minus 0, which is 3. Okay, so this will be my adjoint of A with signs. Okay, with signs. No need to change any signs. No need to. Okay, now one thing is, if you want to write it like if you want to transpose it later on, so as you are expanding here, you just expand like this, then you take the transpose, and that will be the simple, not the adjoint, that will be the normal matrix of the cofactors. Then you will transpose it, and through that you will find the adjoint. So I directly written it to save more time. Okay, now basically how to find the inverse. So basically inverse you can find, just simply finding the determinant. What will be the inverse adjoint of A, we have already found out, which is the difficult part. Determinant is the easier part. How do you find the determinant? Basically you take this matrix, okay, and you try to make zeros. You try to make 0. How will you make 0? Basically you multiply 5 with this and then subtract, so there will be 2 zeros over here. So basically you multiply 5 with this and then subtract, so this will be 0, 5, 10 times 4 minus 10, which is minus 6. 4 minus 10 is minus 6. Then this is 30 minus what? 30 minus minus 1, so this will be minus 31. Okay, so what will be the determinant? Determinant will be 1 3 times minus 31 plus 6 times 4. So 24, 60, 93 minus 93 plus 24, 89, minus 69. Okay, so determinant is minus 69. So my A inverse will be simply this. I will copy this. Okay, so basically I should write over here also that I'm going like a snake. Okay, this also I will write. I have to copy this and I have to delete all this. Okay, so this is the final answer for this question. So again, there is another shortcut for the adjoint of A of diagonal matrix. So for diagonal matrix, it is pretty simple. What is the shortcut? Basically, what will be the adjoint of A? It is the transfer of the cofactors. Okay. So for this, what will happen? So basically, if you find the minor of this, what is the minor of this? This is B times C minus 0, which is BC. Okay, and then you have to choose the sign also, and the sign will be always positive for diagonal elements. You know, 1 plus 1, 2 plus 2, 3 plus 3 are all even. So sign will be always positive for diagonal elements. So you don't have to care about the sign for diagonal elements at least. So this is BC, fine. Now what about the minor of this? You find the minor of this, you cancel this in this. So this is 0 times C, 0, 0 times 0, 0. So if you find the minor of any other element other than the diagonal elements, it will come out to be 0. So we don't even have to take care about the sign. Okay, now we have to take care of the diagonal elements. Now, what is the minor of this? Again, A times C minus 0, so this is AC. And what is the minor of this? A times B minus 0, which is AB. Okay, AB, AC, AD. Now, this is the adjoint of A. What is the determinant of A? Determinant of A is simply ABC. This is the diagonal matrix, simply multiplication of the diagonal elements. So, ABC. Okay, so now, what will be my A inverse? A inverse will be simply 1 by ABC into whole of this. So if I multiply 1 by ABC to all of the elements, this will become 1 by A, this will become 1 by B, this will become 1 by C. So either you remember this or you can derive it in seconds. Okay. You can derive it in seconds. So A inverse is this. Okay. So basically, let's do an example for this. So what will be the A inverse of this if A is given like this? So simply we can directly write it that my A inverse. Okay, you can do the, you can find the adjoint and all those things. I can directly write it. A inverse will be 1 by 300, 1 by 400, and 1 by 500. This is my A inverse. Okay, so yeah, this is about the shortcut for diagonal matrix. Now let's understand few key points about this. So I told you earlier also, if a matrix is singular, then inverse of that matrix won't exist. If a matrix is non-singular, then inverse of that matrix will exist. Okay, now adjoint of a square matrix will always exist. So adjoint will always exist. Doesn't matter if it is singular or non-singular, but like if it is singular, then won't exist. What does singular mean? Basically, determinant of A is 0. I've already told you this earlier. Okay, but so these are things. Okay, but it will always exist. Adjoint of a square matrix will always exist. Doesn't matter if it is singular or non-singular. So here, determinant of A, anything. Okay, so what are the properties of adjoint of matrix? So properties of adjoint of matrix is where n is the order of the matrix. So it is square matrix, so it is n cross n. Okay, now adjoint of A equals to determinant of A into this A inverse. How do you get it? So we get it from the definition itself. So if you remember the definition, of A inverse, this was the definition, right, of A inverse. So just multiply scalar number, we can multiply scalar on both sides, multiply determinant of A on both sides, what you will get? You will get adjoint of A equals to determinant of A into A inverse. So we are getting it from here. Okay, so now what is this telling us? This is telling us A into adjoint of A equals to the adjoint of A into A equals to the determinant of AI. So determinant of A times the identity matrix. So basically, how do you get it? So basically, we got this relationship, right? Now you pre-multiply and post-multiply A inverse on both sides. Okay, you can do that. So basically, if you pre-multiply and post-multiply A on both sides, A on both sides, you will get, if you pre-multiply, then this A and A inverse will get cancelled. Okay, this is a scalar, you can take it outside. So basically, you can take it before the A, and A times A inverse will be identity matrix, and this will still remain. So this is here, and this is adjoint A adjoint of it, and this is the adjoint of. Now if you post multiply, this will become identity matrix, and adjoint of A times A will still be determinant of A times the identity matrix. So this is how you get the pre and post multiply this relationship. Okay, so I'll just tell you this, that let me name this as basically property 1. So I will write, in short, I will write that pre and post multiply determ A on both sides. Okay, so of equation 1. Okay, now what about the adjoint of 0? So adjoint of 0 basically the null matrix. So if you find the adjoint of 0, it will be a null matrix because all the minus will be 0 itself. So it will be a null matrix of order n, obviously. Okay, I forgot to write the order. And adjoint of an identity matrix will be identity matrix because it is like a diagonal matrix and all of them are 1 itself. So 1 by 1 is 1, 1 by 1 is 1. So that's why it is an identity matrix itself. This is also order of n. And adjoint of lambda A is lambda into n minus 1 into adjoint of A. How does this come up? This is a very, very important property. You have to remember this. You have to remember this. So basically, I obviously I don't have time to prove this, but how you can understand this intuitively. So basically, what is adjoint of A? Adjoint of A is basically the cofactor matrix. So in a cofactor matrix, what happens? In a cofactor matrix, what we do? Basically, cofactor matrix has order n minus 1. Why? Because we just eliminate that row and that particular column. Okay, and then we find the minor of that. So that is what we do, right? So we are multiplying the cofactor matrix with some lambda. Okay, some lambda. Hence, what happens for determinant? If we multiply some scalar, it finally gets multiplied with the resultant determinant with the order, with the power of its order. So it becomes n minus 1. Okay, so that is how this happens. So I will not explain this further because obviously we don't have time for all this. So let me this is like this. So let's go to the next property. So again, the next property is simply adjoint of A transpose equals to the adjoint of A whole transpose. So basically, how do you prove this property? So basically what you do is, what you can do, you have this equation, right? You have this equation. This, just hold on a second. This equation, right? What you can do, you can take transpose on both sides. You can take transpose on both sides. So let me take this equation. Let me color this differently. And in here, this equation is already valid. Replace replace A with A transpose. So if you replace A with A transpose, what will happen? Just change. So hold on a second. Let me paste this over. We won't have enough space. If you replace A with A transpose, this equation will become A transpose adjoint of A transpose. Okay, let me just copy this anyways. This is A transpose, this is A transpose, this is A transpose, and this is A transpose, and this is also A transpose. Now what do you know? Determinant of A and A transpose are same. So I can write this as simply determinant of A only. Okay. Now next what we do, and then what we do is take transpose on both sides. Okay. So I will take another, let me name this as equation 2. Okay. Then taking on both sides, taking transpose on both sides. So if we take transpose on both sides of equation 2, so if I take transpose on both sides of equation 2, what will happen? Basically, if I take the transpose, so like this transpose will come inside, and what I told you, transpose, whole transpose AB will be B transpose A transpose. So this will be adjoint of A whole transpose into A transpose should be equals to like this, A transpose adjoint of A whole, just hold on a second, whole transpose equals to this is same only, right? Because like identity matrix transpose is identity matrix itself, and it's just a scalar multiplied determinant of A, so it won't change. So this will be I only. Okay. So yeah, this is what we get. Now from here, what do you understand? What do you understand? Basically, what we can see is like here with this equation, and they're equal, right? This equation and this one. So here A transpose are same, and they are relating to the same thing. So let me write this. Now one may get confused that aren't these equal? Aren't these equal because they are related to the same thing? No, it is the multiplication of these two, right? The multiplication of these two. That's why these and these won't be equal, because AB equals to BA, that may happen, but A may not be equals to B. Okay, so here I will write this, just quick note. AB equals to BA. Okay, then it doesn't mean that A will be equals to B. Not always. Not always. Just hold on a second. Yeah, sorry for the interruption. Actually, someone came at the door. So basically, this was the note I was talking about, that it doesn't necessarily mean that if B equals to BA, okay, because here let's name this as A, let's name this A and let's name this as B, which is equals to my BA also, okay, because these two are same. So it doesn't necessarily mean that A will be equals to B. That's why A transpose will not be equals to adjoint of A, okay. I think many students may get confused with this. So yeah, this is just a brief note that I wanted to give. Okay, so next, like what I was explaining here, this, right, this, that these two things are equal. If we see this, and obviously these mean determinant of A into I, and this also means, like this also means determinant of A into I. So I will equate these and these, okay. So just hold on a second. Yeah, if I do this, so what I can say is A transpose equals to, I'll just copy this. Now if these two are equal, okay, these two are equal because they are mean determinant of A into I itself. So basically these two matrices are equal, same itself, right, same itself. Hence obviously this will be equals to this, okay, because here it's not A into B. Here what is happening here, let's name this as X into Y. So X into Y equals to some X into Z. Now if I multiply X inverse, pre-multiply X inverse on both sides, this will become Y equals to Z, okay. So hence my adjoint of A will be equals to adjoint of A whole transpose. So this is where we get the whole property, okay. So we'll just copy this. Proof, okay. So this is the thing. So yeah, this is how you get this. Now like this is the another property where determinant of adjoint of A will be equals to determinant of adjoint of A n minus 1. So how do you get this? So basically you can get this through this first equation. Okay, yeah, through this equation only. This is the actually main equation. This is a second equation, so I should write this as second equation. So here what you do, you just take the determinant on both sides. Oh no, not cut, only paste. Yeah. So if you take the determinant, right, if you take the, we need to find the determinant of adjoint of A. So basically what I will do is, I will cross this somewhere out. I will take the determinant of this, okay, on both sides, and here also. Now this is I, right, this is I of order n, and some scalar determinant of A is multiplied with this I. So this will become determinant of A into adjoint of determinant of adjoint of A determinant, like these two are matrices, right. Determinant of A times B is determinant of A times determinant of B, that we have already established. So this will be simply, now this is scalar times I matrix. So K times A equals to K raised to power n times I in the determinant format. So this will become determinant of A whole raised to power n into 1, because determinant of I, like I is 1 itself. So basically now I will take this A in this side, and obviously this one will get proved. Okay, determinant of n minus 1. So this is how you prove this one. So again, this is another property, adjoint of AB is equals to adjoint of B into adjoint of A. Now why I am proving you all this, why I am doing the proofs, because sometimes in examinations in simple this matrix type of question, with the help of this proofs, whatever I am doing, whatever steps I am taking, right, these types of steps you have to take during solving these questions also sometimes. So this will help you how to use these steps, right, how I'm taking the determinant, how I'm taking the, I'm multiplying A inverse on both sides, how I'm using the equations. So this may help you build up the intuition. Now this is the next property where adjoint of AB equals to adjoint of B times adjoint of A. So can we prove this? So basically what you can write is, what is adjoint of B times what is adjoint of A. So what is adjoint of B? Adjoint of B is simply determinant of B into sorry, I'm missing. So this was adjoint, like we have already written, right? Adjoint of A is a matrix. Okay, I actually cut it. Okay, no, those can't be cut. Just hold on a second. here, right? Just copy it. By mistake I cut it, actually I need to paste it over here again. So basically I am talking about this equation. The adjoint of A is determinant of A into A inverse. So I will write this here again. Determinant of B into B inverse. Okay. And adjoint of B is determinant of A into A inverse. Now both of them are of order n cross n. Now obviously these are scalars, right? These are scalars. I can take this in front. Okay. These are just simple scalars. So this is determinant of B times determinant of A into B inverse into A inverse. I can write. Okay. Now there is an inverse property. Okay, I will explain later. But okay, let's understand this property also, that if there is some AB, okay, so if I take the whole inverse of this, it will be B inverse into A inverse. I will just prove this just in the next slide. Don't worry, I will just prove this in the next slide. So all of this is representing this AB whole inverse. So also this I can swap, right? They are just scalars. I can swap. I can write A first, then B later, because they are not matrices. They are simply scalars. So here A B, and this is A B whole inverse. Now this A B, right? I can write this in a single determinant. Okay, because they are just simple scalars. So this is simply determinant of AB. Determinant of AB into AB inverse. Now what does this mean? Determinant of something into its inverse. That means it is simply talking about the adjoint itself. So which is equals to my adjoint of AB. Okay. So you can expand this. You can expand this like adjoint of ABC will be simply equals to adjoint of C, adjoint of B, adjoint of A. Okay, adjoint of B, adjoint of B, C, adjoint of A. Okay, so yeah, these are the properties. So there is also another property, the adjoint of A. What will the adjoint of A? It will be equals to determinant of n minus 1 into A. Okay. Yeah, sorry for the interruption. Basically, like I was recording, but I forgot to like start it again. So basically, what I was explaining is that I again copied this second equation, right? Second equation. Okay, second equation I copied, and then what did I do? I simply replaced my A with my adjoint of A. Now if I replace my A with adjoint of A, what will happen? This will be adjoint of A times adjoint of A equals to determinant of adjoint of A times identity will remain same. That is fine. Now next what I'll do? Now what is the determinant of adjoint of A? We have just proved it, which is equals to the determinant of A raised to the power n minus 1. So I can write this equals to determinant of n minus 1. Now what next? Next is what I can do. I can multiply A on both sides. Why do I want to multiply A on both sides? If I multiply A on both sides, this will be again at the form of A adjoint of A, which is here, and which is equals to something scalar type thing. That is why I want to pre-multiply A on both sides. So if I pre-multiply A on both sides, this will become okay. Now it doesn't matter that this is a scalar, we can take it here also. So this A will come here. So this one will become determinant of A times I into adjoint of A simply. And it doesn't matter, I can neglect the I, but that's fine. Just copy this. This I can exchange. Okay. And finally I can divide my, this is scalar, right? I can divide on both sides. So this will become simply this, right? This will become, so I times anything is that matrix itself, adjoint of A equals to my determinant of A n minus 2 into matrix A. I'm dividing, right? So this is the relationship that we got over here, right? Look, I hope this got proven. So I should actually put them all in a box. You can put this in a short notes, right? I used to do this because I used to tend to forget this, so I used to put this in a short notes because like that will help me remember. But if you know the proof, right, from there also you can like get a basic intuition how are this all happening. So yeah, basically these are few properties. So yeah, next property is this one. Okay, next property is this one. I will do one thing. I will give you homework to prove this. Okay, I will write this and I will give you homework to prove this because obviously we're running out of time. Okay, these two properties are there. Okay, you just do one. Just take the determinant on both sides of what? Just take the determinant on both sides of the previous one that we proved. So basically, just take the determinant of this. Whatever I proved over here. If you take the determinant of this, right, you will get your answer. Okay, so yeah, that's how you do it. So basically, let's understand few properties of inverse of a matrix. So if ABCD inverse is given, then it will be D inverse, C inverse, B inverse, A inverse. So it is known as the reversal law. Reversal law. Okay, now how do you prove it? So basically, ABCD inverse is given. So if I multiply ABCD inverse with ABCD, what I will get? I will get the identity matrix. Whatever is inside that, I will get the identity matrix. So basically, I will write this in short over here. So ABCD whole inverse times ABCD, I will get my identity matrix, which is equals to I. Now what I do? I just post multiply these things. Right? I will post multiply D inverse, C inverse, B inverse, then A inverse. So basically, post multiply this. So first I will post multiply D inverse. So just hold on a second, let me copy this, paste this. So if I post multiply D inverse, this will be D inverse, then this will become what? This will become I only, so this will become ABC only. So if this becomes ABC, then I will post multiply C inverse and so on. So if I do this, then my ABCD inverse will be equals to, okay, let me prove it anyways because else you'll get confused. So okay, I may not have space here, so what I can do is I can simply borrow space. So copy this, cut this actually. I'm writing here proof next page. So that's why post and pre-multiplication are very important. So basically this will become I only. Okay, D inverse into D is D into D inverse is I only. So this will still remain ABCD and here, right? And this side this will be D inverse. Now what I will do, I will multiply by C inverse. Okay, post multiply C inverse, then this will be AB. Just doing this in a hurry actually. Inverse into AB, this will again become I equals to D inverse into C inverse. Now what I will do, I will just multiply with B inverse, again this will become I. This will be ABCD whole inverse, and this will be A only. This will be D inverse, C inverse, B inverse, and what I will do, I will multiply with A inverse. So this will become A inverse, and hence proved. Okay, so this is the reversal law. Then if I multiply a scalar with A and then I take the inverse, simply it will be 1 by k, self-explanatory. Where one more condition is important, that my k cannot be equals to 0 obviously. Then obviously it will become a null matrix, and inverse for a null matrix doesn't exist. Now A transpose of inverse equals to the A inverse of whole transpose. You can understand this with the concept of adjoint or something, but like don't need to, you can remember this, right? You take the transpose, then you take the inverse, or you take the inverse, then you take the transpose. They are both same thing, but at the end you're doing the transpose itself, and elements are getting transposed at the start or at the ending, so it doesn't matter. Okay, then A raised to power k whole inverse equals to the A inverse raised to power k. Okay, k means multiplying A matrix 2 times, not simply squaring the elements. I will explain this in one of the questions, there you will understand. Okay, these are few properties, and A inverse of determinant will be 1 by A. This is self-explanatory. Okay, so another property from this is k times A inverse determinant will be simply okay, sorry, this will be, I think, okay, one property mistake I made over here. This will be k raised to power n in the denominator actually. Okay, no, this won't be k raised to power n, because here k is getting multiplied, right? Here k is getting multiplied. If it was another property where, let me write this, some property like this, the determinant of k inverse of this. So okay, I don't have space, so we can again borrow space. So this will be simply equals to 1 by k raised to power n, where n is the order of the determinant. So like n is the order of the determinant. So n is the order of determinant. Okay, so yeah, these are a few things. Basically, if k is multiplied like this, okay, then it will come out k raised to power n, simple like determinant formula, you know, scalar multiplied, it will come out k raised to power n. And if k is multiplied like this, so k is first getting multiplied with this inverse, okay, then we are taking the determinant, then that's a different case. Okay, I should write this like this, sorry, again I made a mistake over it. This inverse, right, inverse will be overall throughout this, inverse will be overall throughout this. Okay, so inverse will over through this, which is 1 raised to power k raised to power n into determinant of A. Okay, so let's what I will do is I will give you this question as homework. Try this, whatever we prove, right, through that you try to do this. Okay, and like you can read the question, and if some matrix is given, then definitely you have to use this some property. And this is also another question that I will give you as homework. Okay, and like this is a very good question, try to give it a good thought about it, don't try to look at the solution, try to give a good thought about it. Non-zero means not null, not null matrix. Non-zero means not null square matrices of size n cross n, and if x times y is 0, then what will be the determinants? Okay, what can be the results? Then which of the following options is /r correct? Okay, so yeah, this is basically it for this lecture, and we'll solve in the next lecture, we'll solve these questions and many more questions, and also we'll do more types of matrices. Okay, we'll finish more types of matrices, like because we couldn't cover those because few properties were left. So we'll finish that, we'll do questions in the next lecture. Okay, so I hope you like this lecture. Thank you for watching, and if you have any more doubts, you can ask in the group section.